Good evening, class. Here's module 1 of pre-calculus covering chapters 1 and 2. Chapter 2, linear functions. As always, an exam starts with a pledge. So before starting the exam, please read the following pledge aloud. I pledge on my honor that I will neither give nor receive unauthorized assistance, so on and so forth. I can't emphasize the importance of that. Now, let's start with a definition. Dependent and independent variables. For an equation in variables x and y, if the variable of y depends on the variable of x, then y is the dependent variable and x is the independent variable. Relation, a set of ordered pairs. Domain, a set of all input values, x values, independent variable for a relation. Range, the set of all output values, y values, or the dependent variable for a relation. Now, how do we find the domain and range if we have a graph? We try to lay it down along the x-axis, whatever it covers is the domain, along the y-axis, whatever it covers is the range, as you can see in both graphs. What's a function? A function is a relation in which each element in the domain corresponds to exactly one element in the range. In other words, the x coordinates cannot repeat, and we check it out with VLT, the vertical line test. If a vertical line can be drawn so that it intersects a graph at more than one point, then the graph does not represent a function. If a vertical line cannot be drawn so that it intersects a graph at more than one point, then the graph represents a function. So simply put, you draw a vertical line. If it crosses it more than once, it fails to be a function. Also, we have a one-to-one function. A function is one-to-one if each element in the range corresponds to exactly one element in the domain. In short, it's a function if the x coordinates don't repeat, and it becomes a one-to-one when the y coordinates can't repeat either. We check it with vertical line test when it comes to be a function. For a one-to-one function, we check it with a horizontal line test, HLT, which indicates if a horizontal line can be drawn so that it intersects the graph of a function at more than one point, the graph is not a one-to-one function. And what you're looking at here, DQ, the difference quotient, in short, is the average rate of change of y with respect to x. One way to write it is f of x plus h minus f of x over h. Needless to say, h can't be 0. All right, let's look at a couple of examples here, starting with the following. We want to find the domain of each function using interval notation. So when we deal with a rational expression, remember, you have to exclude what makes the denominator 0. So the very first thing we do, we set it equal to 0. We find x equals 1/2 makes the denominator 0. And we say the domain x can't be equal to 1/2. Now, can't be equal to 1/2 is one way to write it. In an interval format, minus infinity to 1/2, union 1/2 to infinity, you use parentheses to exclude the endpoint, namely 1/2. So that's pretty straightforward, everybody. Now, what about the square root of 5x plus 4? When the index is even, and remember, when we have an index, the index is 2. So the square root of 5x plus 4. There is a restriction, which means whatever is the radicand, what's underneath can't be negative. It has to be greater than or equal to 0. Non-negative values. That's the idea. So We move this to the other side, becomes -4, and then divide by 5. X larger than or equal to -4/5, or we can write it in a interval format, as you can see here. Because the endpoint -4/5 is included, we use bracket. Bracket means the endpoint is included, everybody. All right, so now what happens in this case? The answers are real numbers from negative to positive infinity. Why is that? Because it's a polynomial of degree 2. More specifically, it's a quadratic function. Every polynomial has a domain which is all real numbers, everybody. Again, polynomial, the degree is 2, everybody. So that's pretty straightforward. We are going to move on. All right. We are looking at cube root of x. And what is the domain here? Because the index is odd, there is no restriction, everybody. It's all real numbers. It's that simple. The domain is all real numbers, and as mentioned, the reason is because the index is odd. Just to illustrate this fact, the idea is as follows, everybody. If we look at, for example, square root of 4, we know the answer is 2, okay? But square root of -4 is not a real number, it's 2i. That's why underneath must be positive or 0. Whereas cube root of 8 is 2, but cube root of -8 is -2, and there's no restriction. So when you have an odd root, there is no restriction. So the answer is all real numbers. Pretty straightforward, everybody. Let me erase
And
my board.
when you
Yes,
say there's no restriction, do
that
you
means
mean
all real
by,
numbers. That means the domain is all real numbers.
and this is the fact that it can be whether negative or positive, it doesn't matter, and this is only when it's cubed root.
When it's an odd, if it's the fifth root, it works the same way. Any odd index will do that. As an example, a cube root.
Okay, thank you.
My pleasure. Again, just to verify that, when you're dealing with roots, this represents the index, the root, okay? When it's odd, no restrictions means all real numbers work. When it's even, has to be non-negative. All right, going back to a rational, you set the denominator equal to 0, and you find out what makes it 0, you exclude that. X squared minus 1 equal to 0. Obviously, x is plus minus 1. So what is the domain? This represents the domain, everybody. How do we write this in an interval format? negative infinity to negative 1, union negative 1 to 1, union 1 to infinity, and we use parentheses. That means the endpoints are excluded. What about f of x equals 2/3 x plus 7? Again, no restrictions, all real numbers. You can say all real numbers are negative to positive infinity. Why is that? This is a linear function. This is a polynomial of degree 1. Degree 1 or 0 is considered linear. Even a horizontal line which has a degree 0 is considered a linear function, because when you draw it, it's a line. We want to determine if the graph represents a function, a one-to-one function, and find the domain and range of each using interval notation. Well, first and foremost, let's look at whether it's a function, it's a one-to-one function. And starting with the first one is both. Yes, it's a function, and yes, it's a one-to-one function. Why is that? Well, can you draw any vertical line that crosses the graph more than once? Can you draw any horizontal line? Vertical line tells you it's a function. Horizontal line, it passes a horizontal line test. It says it's a one-to-one function. Now, to find the domain, you try to lay this along the x-axis, and notice it covers from here to here, from number 2 to number 8. So the domain is from 2 to 8. Is 2 covered? No. Is 8 covered? Yes. The way we represent it, 2 takes a parenthesis, 8 a bracket, because that means now the endpoint 2 is not included. The endpoint 8 is included. What about the range? Now try to lay this along the y-axis. It covers anywhere from here to here. In other words, this is number 6, this is number 8. It covers from number 6 to number 8. Is number 6 included? Yes. What about 8? No. So bracket 6 comma 8 parentheses. That's the range. And it tells you which endpoint is and which endpoint is not included. What about this one? Does it pass a VLT? Yes. It is a function. How about the horizontal line? Just think about it. Look at this horizontal line. It crosses the graph at 2 points. You can come up with many horizontal lines. Is it a function? Yes. Is it a one-to-one function? No. What's the domain? Let's try to lay it along the x-axis. It covers from here to here. This point, -3 is included? Yes. This point, +2 is included? No. So the domain is bracket -3, comma 2 in an interval notation. What about the range? So again, lay this along the y-axis. It covers from here, -5, all the way up to here, +4, and everything in between. So, and the endpoints are both included. Therefore, the answer is bracket -5, comma 4, bracket. What about this one? It's neither a function nor a one-to-one function. Clearly, it fails a vertical line. Let's just pick this up, for example, this one and this one. Oh no, this one and this one. Horizontal line. If you pick any horizontal line, this one and this one. So it fails both cases. It's not a function. It's not a one-to-one function. What about the domain? What does it cover along the x-axis? Clearly from here to here. So let's count 1, 2, 3, 4. So from -4 to 0, okay, and along the y-axis from 0 to 4. The endpoints are included, yes, in both cases. Given the function f of x equals to x plus 1, find and simplify f of x plus h minus f of x over h. I want to go over a couple of things, very important. Number one, rates of change, okay, the difference quotient, delta y over delta x, y sub 2 minus y sub 1 over x sub 2 minus x sub 1, or f of x sub 2, if you look at this one, f of x sub 2 minus f of x sub 1, okay, that's the rise. And this distance is x sub 2 minus x sub 1, or delta x. So delta y over delta x, rise over run. It's the good old slope, and it's called the average rate of change of y or f of x with respect to x over the interval of x sub 1 to x sub 2, and can be interpreted as the slope of a secant line. The blue line is called a secant line. If you have 2 points on a graph, connect them, okay, on a curve, you can easily calculate the slope. Ultimately, one way to look at this is this one, and all of them are really difference quotients. This one more specifically is considered a difference quotient. If you look at this format, and the point, instead of x sub 1 and f of x sub 1, we say a and f of a. The second point, as we move delta x or h to the right, is the run, and this one becomes a plus h. Now this one becomes the function, whatever it is, q at a plus h and f of a plus h. It gives rise to this one. And there are different ways of writing them, everybody. Delta y over delta x. F of x sub 2 minus f of x sub 1 over x sub 2 minus x sub 1. This one, if we call this point b comma f of b, then f of b minus f of a over b minus a. F of x minus f of a over x minus a, if you keep one of them, the first one as a and the second one as x. Why am I going over this? Because in the next course in calculus, you're going to take the limit of this one and let h go to 0. So it's important to be able to handle this and simplify this using your algebraic techniques. That's why we're going to work on this. So f of x plus h minus f of x over h is of interest to us because of what's coming up in the next course. So having said that, what is f of x plus h? Well, 2 times x plus h plus 1 minus, just put f of x and h, and all you have to do is simplify that. Let's distribute. We get 2x plus 2h plus 1 minus 2x minus 1. This one just changes the sign of each term inside, and we notice 2x and negative 2x cancel each other, positive and negative 1 cancel each other. We get 2h over h, and it's 2. Ultimately, in the next course, the process must be in such a way that ultimately you lose the h in the denominator. As you can see, of course, we do. And that's, you have to use your algebraic technique to achieve that. Algebra functions. F plus minus g of x is f of x plus minus g of x. This is called the sum and the difference function. If g of x is f of x times g of x, the product function. F over g of x is f of x over g of x. Needless to say, g can't be 0, and this is called the quotient function. Given the domain of f being a, the function f of x has a domain a, and a domain for the g is b. So we do have a domain for each one, assuming one is a, one is b. Then the domain of all of these functions is the intersection of the two. Okay, it shrinks. Okay, it has to be okay with f and g as well. This one is even smaller because g can't be 0. So we write it in the following manner, the domain for this one. Let me or this one is this. Now, how do we read this? X is an element of A intersection B, this line segment, we read it such that. So let me just quickly, let me quickly read that for you one more time. The domain of F over G is X, and it's all X's as an element of the A intersection B, such that G of X can't be zero. That's what this is all about. So I hope everybody is following this. Now, in other words, the restriction that you expect. What is the restriction? The denominator can't be zero. So that makes it a little bit more precise. So let's erase my work and then we continue. Okay. Composite function, by definition, f of g is f of g of x, g of f is g of f of x. Bear in mind, in this case, the x starts coming from the domain of the g function, whereas this one, it comes from the f function to begin with. Okay. And we have this, and here's the synopsis of what happens. The domain of a composite function, f of g, refers to the set of all possible input values, that means x values, for which the function is defined. The set of values from the domain of the inner function. So we are looking at the first one, okay? And the second one follows in the same manner. The inner function, g of x, that also produces outputs within the domain of the outer function, f of x, when composed. The input value must be valid for both functions involved in the composition, with the output of the inner function needing to be a valid input for the outer product. Meaning what? Inner function is the restriction. As I mentioned here, we start with the domain of this guy, the inner function. So the inner function restriction, the domain of the composite function is always a subset of the domain of the inner function g of x. So if you happen to have the inner function, for example, in this case is g, and the domain is b, the domain can't be larger than b. Maximum, it can be equal to b. And then you have to look at more restrictions. Output check. For a composite function f of g of x, you need to ensure that g of x, the output of the inner function, is within the allowed input of function f of x. So after you restrict it to b, then you check the result. That is the fastest and easiest way. You look at the final function f of g of x. So to find the domain of a composite function, first find the domain of the inner function, then restrict that domain further by considering which output of the inner function are valid inputs for the output functions. I'm going to make some sense out of this as we look at some examples later on. But in short, the inner function is the restriction to begin with. So for example, for this one, we start with the domain of G, which is B, and then we look at the final result. We further investigate the final result, and it tells us whether we have to restrict it further or not. That's really the bottom line. All right. Let's look at a very simple example of composite function. F of x is given, g of x is given, and we want to find f of g of 2. And obviously, when we look at this, we start with g of 2. So what is g of 2? So this function, replace the x with 2. Six minus 5 is 1. That means when we say f of g of 2, we mean f of 1. That's the meaning of it. So now we go back to the f of x function and replace the x with 1. 2 times 1 squared plus 1. And this is 1, 2, and 1 is 3. Pretty straightforward, everybody. What about f of g of x? That means f of g of x. And that means into this function, replace the x with 3x minus 5. So we're going to raise this to this power of 2, reminding you that a plus b squared is a squared plus 2ab plus b squared. And a minus b squared is a squared minus 2ab plus b squared. Also, a squared minus b squared is a minus b plus b. I'm just reminding you of something. So what is this one? You square this one, you get 9x squared. Then the product of those two times 2 is minus their dx. And if you square that, you get 25. So we distribute the 2, we get 18x squared minus 60x plus 50. And these two add up into 18x squared minus 60x plus 51. We're going to continue with that. G O f of x. That means g of f of x, and plug in the f function into g. In other words, 3 times f of x. So 3 times 2x squared plus 1 and minus 5. This, of course, gives us 6x squared plus 3. And so these two add up to negative 2. The final answer is 6x squared minus 2. What about GOG? That means into this function, replace the x with itself. So replace the x with 3x minus 5. Distribute, we get 9x minus 15. These two add up to minus 20. We have 9x minus 20. Now we want to find f or f of negative 2. Simply put, it means we want f of negative 2. Therefore, we're going to find f of negative 2 first. Over here, we're going to put negative 2, which means 2 times negative 2 squared plus 1. Now, of course, this is 4. 8 plus 1 is 9. Now that we found 9, we want f of 9. So we are going to write, so we want f of 9. We are going to write 2 times 9 squared plus 1. 9 squared, 81. So 2 times 81, 162, plus 1 is 163. Determine if the function f of x and g of x are odd or even. Let's remind everybody of those types. Even function, f of minus x equals f of x, and the function is symmetric with respect to WRT with respect to the y-axis. On the other hand, an odd function, f of minus x is minus f of x, and it's symmetric WRT with respect to the origin. So that's the difference, everybody. All right, so let's evaluate f of minus x. Let's evaluate g of minus x and see what we get. So f of minus x. So 2 times minus x quantity squared plus 1. And I hope you see, because the exponent is even, minus x quantity squared becomes x squared. So we get 2x squared plus 1, which is identical to the original function f of x. Therefore, according to this definition, f of x is an even function. Now we're going to evaluate g of minus x, which means 3 times minus x minus 5. This becomes negative 3x. So what happens, you compare it to g of x. Is this equal to g of x? No. So it's not even. Is this equal to the opposite of that? No. Therefore, g of x is neither. So that's pretty straightforward. A quick recap. A function is even or odd, you have to evaluate f of minus x. F of minus x equals f of x, that's an even function. F of minus x is minus f of x, it's an odd function. Okay, so that's how we do this, everybody. Find the average rate of change of each function on the specified interval. In this case, f of x is 3x, and we want to evaluate it from -1 to 1. And I'm going to remind you what we just went over, and I'm not going to repeat that. Ultimately, the average rate of change of y with respect to x represents this concept known as the difference quotient. And there are many different ways of writing it, depending upon how you label your points. In this case, we want f of 1 minus f of minus 1 over 1 minus minus 1, according to this. So what is f of 1? 3 times 1. Minus, what is f of -1? 3 times minus 1. And the bottom is 1 minus minus 1. Needless to say, this is positive 3. So the numerator is 6. The bottom is 1 plus 1 or 2, which makes it 6 halves equals 3. F of x is 2x minus 9. And we want to evaluate the rate of change from 4 to a, which simply put means f of a minus f of 4 over a minus 4. Okay. So the denominator is very straightforward. Let's start with f of a. So that becomes 2a minus 9 minus, how about 4? 2 times 4 minus 9. So this is 2a minus 9. This is 8. And we get minus 1. Negative in front makes it plus 1. And the numerator becomes 2a minus 8. Clearly, you can factor the 2 out. So you get 2 times a minus 4. And the answer becomes 2. F of x is 3x plus 4. And from 2 to 2 plus h. So we want f of 2 plus h minus f of 2 over 2 plus h minus 2. And clearly what happens, the denominator becomes h, and that's what's going to happen in calculus mostly. And so having said that, what is f of 2 plus h? Let's plug in. 3 times 2 plus h plus 4 minus, what is f of 2? 3 times 2 plus 4. We are going to distribute and simplify and see what we get. So this one is 6 plus 3h plus 4. This is 6 plus 4 is 10. So minus 10. So I hope you see that number 6, number 4, number negative 10, they add up to 0. So the numerator just changes to 3h. And obviously, we drop the h and we get 3. Ultimately, you take a limit as h goes to 0. So you're hoping to drop the h. So you want to get very comfortable with this concept, everybody. Graphing techniques, transformations, vertical and horizontal shifts, and so forth. Let's discuss that with this graph. So the function y or f of x looks like that, everybody. If we say f of x plus c, in essence, we are adding to the y coordinate, we move it up. F of x minus c, we bring it down by c units. F of x minus c, we move it to the right, and f of x plus c, we move it to the left. That's the synopsis of what we have here. It shifts right, left, up, down. Also for this one, and by the way, we are assuming c is positive here. Now, for compression, stretches, and reflection, we are assuming c is positive. Again, the same function, y equals f of x. If c is larger than 1, c f of x, it makes it get larger in essence, okay? It stretches along the y-axis by a factor of c. C is larger than 1. On the other hand, if it's 1 over c, it shrinks by a factor of 1 over c, okay? And if you happen to have y equals minus f of x, it flips over with respect to the x-axis if you put the negative in front of the function. However, f of minus x, the same function flips over or reflects with respect to the y-axis. We also have f of cx, where the function y equals f of x shrunk by a factor of c in a horizontal direction, and x over c, it stretches by that factor. We're going to look at a couple of examples to make some sense out of this. So it says the following function was graphed by applying transformation to a toolkit. By toolkit function, we mean essential functions. We mean basic functions. You should know the graph. Write the equation of a function that matches the graph. So What do we do? Well, first I want to remind you of the basic functions we are supposed to be comfortable with. So these are the toolkit functions. We're going to start with the first one. We're going to discuss them one by one. The first one, y equals a number, or f of x equals b, is called a constant function. It's a horizontal line with the y-intercept at 0b. The next one, y equals x, or f of x equals x, we call it an identity function, is a graph of a line that goes through 0, 0. Next, y or f of x equals x squared, or a square function. It's just a basic parabola everybody's familiar with. Next is the cube function, f of x equals x cubed, looking like that. This is the end behavior, the first and the third quadrant. Goes through 0, 0, 1, 1, negative 1, negative 1. The next one is a square root function, f of x, or y equals square root of x, and it looks like that, goes through 0, 0, and 1, 1. Another one is a cube root of x. Looks similar to y equals x cubed. It doesn't rise as fast, of course, goes through 0, 0, 1, 1, and negative 1, negative 1, just like that. What else do I want to discuss? When you have the graph, you know a lot of things about it. For example, let's go back here. You know the y-intercept. You know the domain is all real numbers. The range is only one point P. What about this one? Obviously, you know it goes through 0, 0, so that's your x and y-intercept. Domain and range, both, no restrictions, all real numbers. It's a linear function. So it covers along the x-axis, along the y-axis, everything. This one, 0, 0 is the x-intercept as well as the y-intercept. It covers on a 1, 1, negative 1, 1, and so on. And the domain, it covers the entire x-axis. So it's all real numbers, but the range is from 0 to infinity. So from the graph, you should recognize that. What about here? It goes through 0, 0, which is both the x and y-intercept, domain and range, all real numbers, clearly. This one, similar to that, it goes through 0, 0, which is the x and y-intercept, and domain and range are real numbers. Finally, this one, of course, 0, 0 is both the x and y-intercept, domain from 0 to infinity, range from 0 to infinity. So when you, and of course, 0 is included. When you know the graph and remember the graph, you don't have to memorize any of these things. The graph will tell you what is the domain, range, x-intercept, y-intercept, if you have asymptotes, and so forth. Another function, which is one of those essential functions we are supposed to know, it's an absolute value function, which is a V shape, everybody. So y equals absolute value of x has the vertex at 0, 0. But the vertex is no longer there. Now, here's the transformation we want to discuss. The vertex has moved here, 3 to the right, 2 down. So 3, negative 2. So how do we find the new function, the equation of a new function? We start by writing in this format, class, and you probably remember that for the parabola, that a times x minus h quantity squared plus k. So the methodology is that you write y equals a absolute value of x minus h plus k, and you want to find the vertex. Anytime you have a vertex, you find the vertex and a. Now the vertex is given, so clearly this becomes y equals a times x minus h is 3 plus k minus 2. We are almost there. All you have to do, pick an easy point. Notice these two are easy points, and the coordinates are 1, 0, 0, 1, and you can use one of them. That's all you need. One of them to find the missing a. So for example, if I use that, the y is 0, a absolute value of x is 1 minus 3 minus 2. Now, obviously, this is 1 minus 3, 2. And the absolute value of 2 is 2. 2a minus 2 is 0. It makes a 1. So I'm going to replace the a with 1. And it's really a good idea to check. So how do you check? You pick some other point and you check it. You can go with 0, 1 or some other point. For example, 0. If I plug in 0, I get minus 3. Absolute value of minus 3 is positive 3 minus 2. Is that 1? Yes, I just check. So whenever you're done, make sure you check. It doesn't take long. The following function was graphed. Again, the same thing, applying transformation kits and so forth. Write an equation of the function, and you're given that. So what do we do? I hope we notice that this looks similar to f of x equals square root of x, and we take it from there. So obviously, we have 0, 0 as the x and y intercept, and now it has moved to a different location. And this is 1, 2, 3 to the left, 1 down, negative 3, negative 1. This is the new location, everybody. So it has shifted accordingly, which simply put means 3 left, 1 down. And again, I'm going to go with the same format. You see this one, I put a square root of x minus h plus k, because in essence, this is not a vertex. You can think of it that way. And so I'm going to replace it, and I'm going to write y equals a square root of x minus 3. That means plus 3 plus k minus 1. And all I have to do, plug in some pair, pick up a pair, and obviously you want to go with something extremely easy. Clearly, we can read this as negative 2, 0, or perhaps this one as 1, 1, and you just plug in. So I'm going to replace the x with negative 2, y with 0. As you know, this is 1, right? Because minus 2 plus 3 is 1. Square root of 1 is 1. So a times 1. A times 1. So a must be 1. And you replace it. And this is what you get. And you really have to check. So how do you check? Go with an easy number again. This one is easy. Clearly 1. 1. So if I plug in 1, I get 4. Square root of 4 is 2. Minus 1 is 1. Yes, it checks, and I'm done. All right, again, the same question. The following function was graphed, applying the transformation to a toolkit, and you want to write an equation for the function. This is given, and I hope you recognize that as a parabola, of course. So we are dealing with this, and the vertex, which is at 0, 0, has shifted here. Okay, and that has location minus 1, 2. So y is a times x minus h quantity squared plus k. So we are going to write y equals a times x minus h. X minus 1 is plus 1 quantity squared plus 2. Okay. And now we pick another point. It doesn't matter which one. You just want to make sure it's an easy point. Clearly, this is located at 0, 1. Easy point. Something that you can clearly read. So we're going to replace the x with 0 and y with 1. So this is 1, square root is 1. So this is 1. So a plus 2 is 1, and it makes a negative 1. So you replace it, and this is the function. Now, needless to say, we have to check, and I highly recommend you go with the easy numbers to check. For example, this one seems to have the coordinates -2, +1. So if I put -2 and 1, I get -1 squared. +1, this makes it negative, and 2 becomes +1. So it works. And that's the idea. You check and recheck always. If you have any doubts, another point in any way. Find the equation of a function that is finally graphed after the following transformations are applied to y equals x squared. So we start with this, and we say, okay, given y equals x squared, we want to shift it 3 units to the right. So we replace the x with x minus 3. So f of x becomes x minus 3 squared. Now reflected about the x-axis, so we put a negative sign in front of this. So f of x equals minus the parenthesis x minus 3 quantity squared. And finally shifted down by 2 units. So we're going to add -2 or you subtract 2. So f of x becomes minus the parenthesis x minus 3 quantity squared minus 2. Those are the transformations, 3 transformations that give us the new function. And it's done.